Hello everyone, welcome back. In today's video, I would like to discuss cylindrical coordinates. Cylindrical coordinates is something we may have touched upon briefly at the beginning of the course, but it's something that we really need to refresh on for our triple integrals. Now, this is one of two alternative coordinate systems that we can have for triple integrals. So the first is cylindrical coordinates and the second is spherical coordinates, which we'll cover in the next video. They're kind of analogs to the polar coordinates in 2D integrals, but of course, for 3D integrals, we can have some more generalization. Either we can use a cylinder or a sphere as our main alternative coordinates to rectangular coordinates. Now, we're not going to do any examples, but I do want to outline how you solve the problems and consider the applications that may arise herefrom. Now, if I have a cylindrical coordinate system, I'm going to be defining multiple quantities. So we're essentially defining 3D polar coordinates. We define x as being our cosine theta, y as being our sine theta, and z being z, right? So if I graph out my xy plane, so that's my xy plane there, and then I draw out a unit circle, right? I can sweep out the whole xy plane simply by defining r and theta, right? However, if I want to take this into the third dimension, into the z dimension, all I'm going to do is add a z component, and the z will go up this way. So as we can see, what we can do here is we can pretty much define a cylinder of any height, of arbitrary height, and assign it an r value, a theta value, and a z value. And if I use xyz over to r theta z, we can sweep out the whole 3D space. This is very helpful to have. And of course, the polar conversion formulas are fairly simple. They're a little bit more complicated for spherical, but we'll cover that in the next video. And of course, if you want to go the other way, you can find r squared by using the Pythagorean theorem, which is just x squared plus y squared. And likewise, you can find tangent of theta by being y over x, right? So if I have a triangle here, and there's my y, and there's my x, and there's my theta, and there's my r, I can go between x and y, and r and theta. And of course, z is trivial because it just goes to z, right? However, what happens if I want to perform an integral, perhaps, in cylindrical coordinates? So if I want to do this, I can consider two cases. I consider the case where I have a region and a function of x, y, and z. If I have a region and a function of x, y, and z, but the region is defined better in cylindrical coordinates, then I will convert the function of x, y, and z over to cylindrical coordinates. The other option is you're just given a function of r and theta and z instead of x and y and z. So that's when you would use the cylindrical coordinates. It's all about using the coordinate system that's going to make your life easier when you're performing out these integrals, right? So let's say I want to take the integral over a function x, y, and z over some volume and some region E. Then I can convert this into polar coordinates and say that we are going between arbitrary functions of theta and arbitrary functions of r. I can take the integral between alpha and beta, which is my theta, alpha between my heights, and the integral between my r variables. So I would have u sub 1 and u sub 2, all of r cosine theta and r sine theta. And of course, I need to convert my function into the correct form, so f of x, y, and z would obviously go to f of r theta and z. But of course, you use these conversion formulas to determine what you're integrating over, right? Now, what I would like to do now is kind of just cover an application. So say I would like to find if I have a cylinder, obviously this is going to be a very easy example, but let's say I have a cylinder. It's of height h and radius r, right? So let's say I want us to find the moment of inertia of this, if this is rolling around or about a certain axis, right? Say it's about that axis. Anyways, you would be integrating a density function dv. So the definition of inertia is I is the integral of r squared dm. However, you write dm is equal to rho dv, and let's say that there's some density rho in this cylinder. Anyhow, how I would set this up is I would have an integral, and my first integral would be the theta integral, or I could do the z integral. Let's do the z integral. If I do the z integral, I go from 0 to h. And then if I do the theta integral, I go from 0 to 2 pi, obviously, because I'm sweeping out the whole thing. And then for the r integral, I go between 0 and r, because I'm sweeping out the whole volume, or the whole radius, right? And then this is of some function rho dv times whatever r squared you have, r squared rho dv, or something like that. And then your dv is going to be dr. Your dv is going to be r d theta dz. Now, it's a little bit complicated, but as you can see, these integrals become a lot easier, especially when your functions are not of the same variable. If you can separate them by multiplication, you can do integral between 0 and h of dz if there's a function of f of z, and then integral between 0 and 2 pi of d theta, or whatever function of theta you have, and then you do the integral between 0 and r of dr, or r